The transition to electric passenger cars is well underway, but vehicles forming the backbone of the global economy are still tied to liquid fuels. Current battery technology is too heavy and drains too quickly to power them. Massive cargo ships, jumbo jets, and 18-wheelers require immense concentrated energy density. Only liquid fuels pack enough power per gallon to move hundreds of tons across oceans and continents. This chart projects transport energy consumption for 2050. Even with aggressive electrification, internal combustion heavy vehicles are expected to consume more than half of all energy used in the transport sector. Relying on fossil-derived petroleum for this massive share of energy continues to drive millions of tons of greenhouse gas emissions into the atmosphere every year. The global supply chain requires liquid fuel to function, but the environmental cost is unsustainable. Breaking this reliance requires finding a biological alternative that matches the power of petroleum. The diesel engine was never actually meant to run on fossil fuels. When the pioneering German engineer Rudolf Diesel invented his engine in 1895, he intentionally designed it to run on biological sources, demonstrating early models using pure peanut oil. These early, massive mechanical systems were designed to function entirely on agricultural plant power. The discovery of cheap, abundant, and easily refined petroleum sidelined diesel's vision, creating a century-long dependence on fossil fuels. Modern biodiesel resurrects this initial concept. It is a renewable, biodegradable replacement fuel that drops directly into modern engines and can cut life-cycle greenhouse gas emissions by up to 86%. Replacing petroleum with plant-based fuel offers an immediate bridge to decarbonize our heaviest machines, using the infrastructure we already have. The foundational chemical requirement for making biodiesel is a heavy fat or oil, chemically classified as a triglyceride. Extracting these oils from edible crops like soy, palm, or sunflower introduces a direct conflict. Agricultural land must either feed growing populations or power global supply chains. To alleviate this pressure, the industry scavenges waste products. Millions of gallons of animal tallow from processing facilities and used cooking oil from restaurants are collected, filtered, and recycled for fuel. A cutting-edge feedstock is microalgae. These organisms produce massive oil yields while multiplying in contained environments, requiring absolutely no arable farmland. Finding the raw fat is only the first step. This crude biological sludge must be chemically engineered to mimic the exact physical properties of fossil fuels. Raw triglyceride molecules are thick and highly viscous. They are simply too heavy to burn cleanly in modern precision engines. This flowchart details transesterification, the overarching chemical process utilized to break down and refine raw fat into crude biodiesel. The heavy triglyceride must be reacted with an alcohol, usually methanol, in the presence of a catalyst such as sodium hydroxide or advanced zinc oxide nanocatalysts. The catalyst attacks the chemical structure, severing the bonds that hold the heavy triglyceride together. This process yields 3 lighter fatty acid methyl ester molecules, which is the biodiesel itself, while leaving behind glycerol as a byproduct. This specific chemical conversion transforms unusable grease into a highly calibrated liquid fuel. Once injected into an engine cylinder, the chemical properties of this biodiesel determine how it behaves under pressure. Biodiesel contains up to 11% oxygen by weight. This built-in oxygen ensures a cleaner burn, provides better lubricity for engine parts, and drastically reduces the amount of particulate matter exhausted from the tailpipe. The fuel does have physical limitations. Higher saturation improves stability, but causes the biodiesel to gel in cold winter weather, forcing engineers to constantly balance cold flow against shelf life. The next chemical evolution addressing these limits is hydrotreated vegetable oil, commonly known as renewable diesel. Instead of using alcohol, this process treats the oils with hydrogen gas and extreme heat. This completely strips away the oxygen, resulting in a perfect chemical clone of fossil diesel that bypasses cold weather gelling entirely. Through these advanced processes, engineers can perfectly replicate the combustion profile of petroleum without pulling additional carbon from deep underground reserves. Biodiesel is currently integrated into our transportation networks, mostly invisibly, operating in B20 blends, a mix of 20% biodiesel and 80% petrodiesel, which helps fleets meet emissions regulations without changing their engines. This map displays 171 commercial biodiesel production plants across the United States, showing the expanding footprint of the industry over the last 2 decades. The remaining challenge is one of sheer scale. Replicating the agricultural footprint, logistics, and refining infrastructure necessary to dent the global petroleum empire requires staggering industrial coordination. Biodiesel serves as a biological recycling system. It proves that powering our heaviest machinery can be achieved by harnessing the chemical energy already growing on the surface of the Earth.